All right, class. Okay, all right. Man, y'all horrible at this. All right, okay, so back by popular demand, me making a fool of myself and trying not to make too many mistakes. So, glory of video recording is you might be able to edit, but you know, who got time for that? All right, okay, related rates problems. So this is, like I've been saying, I used to hate this. I used to hate it with a passion. I really did, because it didn't make sense to me. And then one thing that I changed, that I did, which actually made everything finally click. So we're talking like in the last 5 years. I've been teaching this for 7 years. And in the last 5 years, it finally like hit on me. I'm like, oh, okay. So the issue, okay, one thing is try to write out everything. Every little thing you have. And it works out. It all works out. You'll see it. It's like, it's pretty. All right, we approach related rates problems by writing an equation involving time-dependent variables. So this equation is often obtained by investigating the geometric and or physical condition posed by the problem. We then differentiate the equation with respect to time and obtain a new equation that involves the variables and their rates of change with respect to time. A golfer hits a ball into a pond of water, causing circular ripples as shown in the figure. Radius of the circle increases at a constant rate. Ooh, this is important right here. There is a constant rate. So, constant rate. So, the radius. So, let's take a look. Let's start off with a couple things I know. It's a circle, right? Okay. So, let's see, a couple things that we could actually figure out about the circle. So now, if this is a circle, I could find the area, right, with the radius. And I could also find circumference, right? Yes, the distance around, right? Okay. So let's see what this one's asking for. How fast is the area? Ooh, hey, look at that. There it is. Area of the circle. So let's just start out with the formula. Area of a circle. So my area, pi r squared. So now, what variables do I have here? I have a radius. What about an area? It's an A, isn't it? It's still an unknown value, isn't it? So a couple things I'm going to have. I know because I have this and this, so since I have that, I know I'm going to have an A. I'm going to have an R. I'm also going to have a dA, dr. I'm also going to have a d, oh wait, no, not dA, dr. We already even said with respect to time, dt, and I'm going to have dr, dt. So, the way that I read this right here is that the area, dA, the area is changing, so dA dt, with respect to time. So my area is changing according to some time. Okay, and over here, dr dt says that the radius is changing with respect to time. Is time a variable in here? It's not, is it? No. So, okay, we're going to have to try and account for that. So how fast is the area of the circle increasing when the radius of the ripple is 2 meters? Okay, so it's asking for how fast, okay, is the area of the circle increasing? So what is my end result of this problem I'm going to ask for? Very good. dA dt, right? So this is what I'm looking for. So this right here is my final result. That's going to be my final result. So if you notice, I went through, I labeled everything. I like everything I could there. And listing out what I have. So what do you think that 0.5 ms mean? The radius of the circle increases at a constant rate of 0.5 meters per second, right? So, constant rate, so that's a rate of change, isn't it? That's the rate of change in my radius, isn't it? So I'm going to use that for my dr/dt. So it's going to be 0.5 meters a second. And area of the circle increasing when the radius of the ripple is 2 meters. Right? So I could do 2 right here. Now let's go through and look to see what can I find from here. I'm going to start by, I know I have an A here too, right? Can I find the area? Yeah, I can find the area. Area is going to be simple. Okay, just plug in 2 and it's going to give me the area, the A for this. So if you notice, I'm going through, I'm just cleaning up and going through and filling in what I have right here. This is so helpful doing this. So if I plug in 2, that's going to be 4, right? So my area is 4 pi. And in calculus, just leave everything in terms of pi. It really saves you a whole bunch of time. Unless it is the calculator portion of the test, leave it in terms of pi. So, and that's going to be in meters squared? Yeah, meters squared. So let's take my A. So area is pi r squared. Now let's take the derivative of this. If I take the derivative of A with respect to time, what would I write? dA dt, very good. So when I take the derivative of A, it's going to be a dA, right? dt. Because I took the derivative of something that is not time, right? Okay, if I had a t in this problem, wouldn't that just be whatever the derivative of that t is, right? Kind of like when I had the derivative of, so it was like a dy dx, and it was like x plus y. So when I took the derivative of a non-x, I would have to put dy dx, right? So this is the same concept, and that's why we went over that already. So dA dt, so now let's go ahead and take a derivative. So pi is a number, right? It's a constant. So I'm not taking a derivative of that. I'm taking a derivative of the r. So that's going to give me 2 pi r. But since I took the derivative of r with respect to time, I need to write that. So dr dt. And now let's plug in the information that I know. What information do I know? I know the r, and I know dr dt, right? So my dA dt is equal to 2 pi times 2 times 0.5. So my dA dt is going to be 2 pi. And that is going to be in meters squared per second. Yes. Because area is meters squared, right? Say yes. Yes. Area is square units. So it's a meter squared. So that's meters squared per second. Yeah, don't put per second or second squared unless you're doing the acceleration. And that's it. So what is this actually saying? This is saying that when my radius is 2, at that moment that my radius is 2, it is increasing at a rate of 2 pi meters per second. So that's the area is increasing by that amount per second. Yes? Okay, and that's pretty straightforward. You're always going to get stuff like this. Right here. Answering free response question, be sure to include correct units to receive full credit. So, straightforward, right? I know it's kind of a strange concept, but it's word problems with a lot of other stuff. Just list everything that you have, everything that you know. Step 1, read the problem carefully, perhaps several times. Pay particular attention to the rate you are asked to find. That's what we did. We listed. I put a question mark next to the one that I'm looking for. Okay, if possible, draw a picture, illustrate the problem. We had one. So identify the variables, assign symbols to them. We did that. I listed everything. Label the picture, identify the rates of change as derivatives. Be sure to list units for each variable and each rate of change. Indicate what is given and what is asked for. That's what we did. Write an equation that relates the variables. It may be necessary to use more than one equation. We will have some like that. All right, differentiate both sides of the equation. Substitute numerical values for the variables and the derivatives. Solve for the unknown rate. It's exactly step by step everything that we did. Spherical balloon is inflated at a rate of 10 meters cubed per minute. Okay. So meters cubed, what does that tell me I'm using? Volume, right? Yes, volume. I have the volume. So that's what I'm looking for now. Okay, I have the volume. Find the rate in which the surface area of the balloon, what does surface area mean? No, not circumference. Is it an area? Surface area, it's an area, isn't it? Okay, so now we're dealing with area and volume. Okay, that's important. Of the balloon is increasing. So the area of the balloon is increasing when the radius of the sphere is 3. Okay, so a couple things we need to start off with. I know it's going to be meters cubed, so I need a volume. So I need to know what the volume of a sphere is. Anyone recall? Yep. And anyone recall what the surface area of a sphere is? 4 pi r squared, right? All right, so let's go through. I'm going to start listing what I have and what I know. So I know over here I'm going to have an A and an R, right? So I'm going to have a dA dt. I'm going to have an A, right? And I'm going to have an R. And I'm going to have a dr dt. So since both of these are one problem, aren't they? So the R and the dr dt should be the same, shouldn't they? That's important. Okay, so let's look at this next one over here. So given the volume problem, I know that I'm going to have a, yeah, so how do I say that? I start with a V, right? What else do I have? Is that a variable? Say yes. Yes. It is a variable, so therefore I should have dV dt. So that's going to be important. So it's dV dt. And I'm also going to have my R, right? I'm going to have R. And I have dr dt. Okay, so now let's go through and start talking about what I have. So I know the spherical balloon is inflated at a rate of 10 meters cubed per minute. So that's going to go for my dV dt. That's super important. So because it's meters cubed, I know that's a volume. So I have okay. And find the rate in which the surface area of the balloon is increasing when the radius. Okay, find the rate in which that the surface area is increasing. So what does that mean I'm looking for? So find the rate in which the surface area, so that would be what? Rate of the surface area, right? So the rate of the surface area here is dA dt. So I'm looking for this one. When the radius of the sphere is 3. So I know that is my radius. So R is equal to 3. Okay, so now I think my notes already has a blank page, but no, it doesn't have a blank page. So insert page after. There we go. Okay. So I'm going to do the derivative. So I'm going to start with my A equals 4 pi r squared. So dA dt is equal to 8 pi r dr dt. Okay, so let's do the other side now. So the next one's volume, right? Volume is 4/3 pi r cubed. So dV dt is going to be 4 pi r squared dr dt. Okay, so let's see, what other information do I have? So let's start plugging in what I know, and let's see what I end up with. Plug in what I know. I know that R is 3. So R is going to be 3. Okay, so right here it's going to be 3 squared. Do I know dr dt? Nope. And 4 pi. Do I know dV dt? Yeah, so I put 10. Right? Okay. Let's go over to this side. So I'm looking for dA dt, aren't I? So I'm looking for dA dt, so I'm going to write that out. So dA dt is equal to, now I know R is 3, but no, do I know dr dt? So it's going to be 8 pi 3 dr dt. By writing out everything and showing this, can you identify what do I have to end up doing here? Yeah. What am I doing here? Get dr dt by itself, right? So I'm going to find dr dt from my equation on the right and then plug it into the equation on the left. Again, by listing out and showing everything, you make it super obvious because everything is out there. Everything. So this is going to be 9 times 4 is 36. So it's going to be 10 over 36 pi is equal to dr dt, right? Because I'm going to divide both sides by that 36 pi. So I get that by itself. So now I'm going to replace this dr dt right here with my 10 over 36 pi. So now 8 times 3, so dA dt is going to be 24 pi, right? And that's going to be times my dr dt, which is 10 over 36 pi. My pi's will cancel. Let me see, 24 over 36 is going to be, let me see, that's a 9, 4, 4, 6, 60, 60 over 9?
240 over 3.
Yeah, I understand that. I'm trying to reduce it though.
20 over 3.
20 over 3? Yeah. Okay, so yes, we get 20 over 3 because my pi's will cancel. And this is a factor of at least 6, 12. That's 2, that's 3, so 20 over 3. Yeah, and that's going to be my dA dt. Now, so we're talking about area, right? Area, my units are always square. So my units in this case was what? Meters square per, what's my rate of change time? Minute. Here we go. So that means that the area, the surface area of the balloon, as it is being the rate that it's being increased at, is changing. So at 3 minutes, no wait, radius is 3, right? So when r is 3, so the radius is 3, not time, it's going to be 20 over 3 meters square per second. So that's what the rate that it's increasing. What if this was negative?
It's decreasing.
So the balloon would be getting smaller, right? So that's what I would have. So if it was negative, it would be a negative rate. So it would be decreasing. You guys feel pretty good about this? Okay, good. All right, so I'm going to stop right here. These next problems, I'm going to save for tomorrow. We actually are doing this unit for the next 4 days. So, all right. Don't forget, like, share, and subscribe. It leaves us with like 50